now we're going to talk about the p-series test. The p-series test is used to tell whether a series is convergent or divergent. The p-series test says that the power of the denominator is greater than 1 more than the power of the numerator, then the series is convergent. Now let's see what that means. So here in this first series we see that the power of the denominator is 2, the power of the numerator is 0, so if we take 2 minus 0, 2 is greater than 1, so this series converges. Let's do it with the second one. The power of the denominator is 3.5, the power of the numerator is 2, therefore if you take the bottom minus the top you get 1.5, that's greater than 1, so this one converges. Now let's do the bottom one. The power of the denominator is 1, the power of the numerator is 0, 1 minus 0 is 1. Well, according to the definition, it has to be greater than 1, not greater than or equal to, so this one diverges. But we're going to put a star by this one because we're going to talk about it later in the video. We'll come back to that one.
Next, we're going to look at what a harmonic series is. What a harmonic series is when the denominator follows an arithmetic progression such as 1 over 2, 1 over 3, 1 over 4, and so on. Now this is an example of what the first harmonic series is, 1 over n. This example will diverge due to the p-series test. A harmonic series is often known as the divergent infinite series.
So now let's explore alternating harmonic series. This right here is the alternating harmonic series for 1 over n. This converges, it's an alternating series, and it's a harmonic series. And this is because of these three conditions. The first series shown in our video, 1 over n, is conditionally convergent. So now we're going to investigate the relationship between absolute and conditional convergence. If the sum of a sub n is divergent and the alternating sum is convergent, then we call this series conditionally convergent.
Now, a series would be considered absolutely convergent if both the sum of a sub n and the sum of the absolute value of a sub n are both convergent.
Now let's take a look at this graphically. 1 over n is modeled by the red runner, while 1 over n squared is modeled by the white runner. Due to the p-series test, we know that 1 over n squared converges, but 1 over n conditionally converges. This is because 1 over n squared reaches 0 much quicker than 1 over n.
Now that we know the difference between conditionally and absolute convergence, we're going to work out a few problems here. I'll give you a few moments to solve these two problems, which relate to the question, does the series conditionally converge, absolutely converge, or neither? So let's take a look at this first problem real quick. If we were to approach this with the p-series test, we'd look at the power of the denominator, which is 1/2. And the power of the numerator would be 0, which would equal 1/2, which is less than 1. And because of this, the series would diverge. However, if we were to look at the alternating series, -1 to the power of n over root n, this would converge. So therefore, the series 1 over root n conditionally converges. Now I'll give you a few seconds to work out the second problem. This problem is really easy to do because all we need to do is use the p-series test. So if we were to look at the power of the denominator, that would be 3, and the power of the numerator would be 0, which gives us 3, and that's greater than 1. So this series absolutely converges.
So now, let's sum up how we check for convergence. We use these 3 steps in order to check for convergence. First step is to check for absolute convergence, using the p-series test. If the series absolutely converges, we don't need to go on to steps 2 and 3. If it diverges, we check if the nth term goes to 0. All this means is as you take it out to infinity, does the denominator increase faster than the numerator? If this is true, we check step 3, which is the alternating sum. If the alternating sum converges, We call this conditionally convergent.